What if I told you that everything we can see in the night sky, every swirling galaxy, every glittering star cluster, is just the tip of the cosmic iceberg? That the universe we observe is like a shadow puppet show, where the real actors remain hidden in the dark, pulling strings we can barely comprehend. This isn't science fiction, it's the unsettling truth astronomers face every day. Take this, for example. Galaxies spin so fast that their stars should be flung into the void, torn apart by their own motion. But they aren't. Something invisible, something colossal, holds them together with an unseen grip. That something is dark matter, the universe's best-kept secret, woven into an architecture so vast it defies imagination. Picture a spider's web spun across billions of light years, its silken threads connecting galaxies like dewdrops in the morning sun. This is the cosmic dark matter web, an invisible skeleton stretching across the cosmos, shaping everything we see while remaining utterly undetectable to our eyes. But here's where it gets stranger. This web isn't static. It pulses with hidden forces, warping space itself, bending light into funhouse mirrors, and dictating where galaxies can even exist. And despite decades of research, we've only scratched the surface of its mysteries. Why does dark matter refuse to interact with light? What lurks in the voids between its filaments? Could it be hiding dimensions beyond our own? That's exactly what we're diving into today, 25 jaw-dropping enigmas of this cosmic hidden realm. From ghostly particles that pass through you like you're not even there, to colossal collisions between invisible giants that send shockwaves through the fabric of space. We'll unravel why some galaxies move as if tugged by unseen hands, how dark matter might hold clues to the universe's ultimate fate, and whether we're on the verge of cracking one of science's greatest puzzles. So buckle up, because by the end of this journey, you'll never look at the night sky the same way again. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And the darkest corners, they're about to get a lot brighter. The first great mystery begins with something astronomers call the missing mass problem, and it all starts with a simple question: why don't galaxies fly apart? Think about a merry-go-round spinning at a playground. The faster it goes, the harder it is to hold on. Now imagine that merry-go-round is a galaxy with billions of stars whirling at unbelievable speeds. According to Newton's laws, all that visible matter, the stars, the gas, the dust, shouldn't be enough to keep everything bound together. The outer stars should be flung into the void, lost forever. And yet they aren't. This cosmic conundrum first cracked open thanks to Vera Rubin, an astronomer who dared to challenge the universe's balance sheet. In the 1970s, she meticulously mapped the rotation of galaxies and found something impossible. Stars at the edges were moving just as fast as those near the center, defying gravity's rules. It was as if the galaxies were wrapped in invisible hands, holding them together against all odds. Rubin's work didn't just hint at dark matter, it screamed that something fundamental was missing from our understanding of the cosmos. But here's where the debate gets heated. Some scientists argue that maybe we don't need dark matter at all, that instead, gravity itself behaves differently on cosmic scales. This idea, called modified Newtonian dynamics, or MUND, suggests tweaking Newton's laws to explain those strange rotations without invoking hidden matter. It's a radical proposition, like claiming the rules of chess change when the board gets too big. Supporters point to oddball galaxies that fit MUND predictions better than dark matters. Skeptics fire back: if MUND right, why do galaxy clusters still seem heavier than what we see? The truth is, both sides are chasing shadows. Dark matter believers scour the skies for faint signals of ghostly particles, while MUND defenders refine their math to explain every cosmic quirk. And between them, a universe that refuses to give up its secrets easily. One thing's certain: whether it's unseen matter or rewritten gravity, the mystery of the missing mass isn't just about what's there. It's about how little we truly understand the fabric of reality itself. If the universe is a grand cathedral, then dark matter is the scaffolding that holds up its vast, glittering ceiling, an invisible framework shaping everything from the tiniest dwarf galaxy to the largest superclusters. This isn't just gravity at work, it's gravity with a blueprint. Imagine pouring syrup onto a pane of glass and watching it slowly spread into delicate, interconnected threads. That's how dark matter behaves on a cosmic scale, forming a labyrinth of filaments stretching billions of light years, with galaxies clinging to them like beads on a string. Supercomputer simulations like the Millennium Run have given us a front-row seat to this hidden architecture. Picture trillions of particles dancing to gravity's tune over eons, condensing into a web so precise it predicts where real galaxies should be. These simulations reveal something startling. The universe isn't random. It's organized, with dark matter acting as the ultimate cosmic contractor, directing where gas pools, stars ignite, and galaxies grow. But between these filaments lie the void's regions so empty they'd make a black hole seem crowded. Take the Boötes void, a spherical desert nearly 300 million light-years wide, containing just a handful of galaxies. Step inside one of these voids and you'd see almost nothing in every direction, as if the universe forgot to furnish entire neighborhoods. Yet even here, dark matter's whisper-thin tendrils stretch across the gulf, stitching the cosmos together. Now zoom into the opposite extreme, a place like the Coma Cluster where thousands of galaxies swarm like fireflies in a jar. The gravitational pull here is so fierce it bends light into arcs, a phenomenon called gravitational lensing, revealing the cluster's true weight, mostly dark matter. It's in these dense knots that the cosmic web's power becomes undeniable, proving dark matter isn't just present, it's in charge. What's eerie is how much we still don't see. The web's finest strands might host dark galaxies, structures made entirely of this mysterious substance, with no stars to betray their existence. Some could be drifting through our own Milky Way right now, invisible ghosts passing unseen. And the voids, they might hide even bigger secrets, like pockets of rogue dark matter moving to its own rhythm, untouched by the gravity of galaxies. One thing's clear, dark matter doesn't just lurk in the shadows, it builds them. Every filament, every void, every cluster is a clue to a puzzle we're only beginning to assemble. And with each new simulation, each deeper observation, we're not just mapping the universe's skeleton, we're learning how it breathes. Imagine two titanic swarms of galaxies, each with hundreds of members, barreling toward one another at millions of miles per hour. When they finally collide, it's not the stars that clash, they pass right through each other like ghosts, too far apart to touch. The real drama happens with the clouds of hot gas trapped between them, which slam together like cosmic fenders glowing white-hot in X-rays. But when astronomers pointed their telescopes at one such collision, the now famous bullet cluster, they caught something that shouldn't have been possible. Here's the shocker. When they mapped the cluster's mass using gravitational lensing, the way its gravity bends light from distant galaxies, they found the bulk of the mass wasn't where the gas was. It wasn't even near the visible galaxies. Two huge clumps of invisible something had sailed clean through the collision, leaving the gas behind like smoke from a gunshot. This was dark matter caught red-handed, behaving exactly as predicted. A gravitational anchor unaffected by the forces that stalled ordinary matter. For dark matter skeptics, the bullet cluster became a nightmare. Alternative theories like MUND, which tweak gravity to avoid invoking unseen particles, struggle to explain why the lensing signal divorced itself so cleanly from the visible stuff. If gravity alone were responsible, the mass should have followed the gas, not forged ahead like a runner ditching their backpack. Yet there it was, a cosmic crime seen with dark matter's fingerprints all over it. But science never rests. MUND supporters have proposed workarounds, suggesting unseen streams of mass or subtle gravitational effects could mimic the signal. Others point to stranger possibilities. Could dark matter itself interact in ways we don't yet understand? The bullet cluster remains a smoking gun, but the trial isn't over. Every new collision we study, like the musketball cluster or El Gordo, adds another piece to the puzzle. Some align neatly with dark matter's story, others, well, let's just say the jury's still deliberating. What makes this mystery so thrilling isn't just the proof it offers, it's the questions it leaves dangling. If dark matter really is a particle, why does it ignore everything but gravity? Could there be multiple types, some more sociable than others? And what happens when we find a collision that doesn't play by the rules? The bullet cluster didn't just validate an idea, it turned the hunt for answers into a high-stakes game of cosmic forensics. If dark matter were a criminal, it would be the most slippery suspect in cosmic history, leaving behind mountains of circumstantial evidence but never a clear fingerprint. For decades, scientists have been chasing its identity through particle colliders, underground labs, and even Antarctic ice, testing one tantalizing theory after another. At the top of the list, WIMP, weakly interacting massive particles. These hypothetical heavyweights are the prime suspects because they fit so neatly into existing physics. Picture a neutrino's shy cousin, but with enough mass to explain dark matter's gravitational grip. Theories suggest they'd rarely bump into ordinary matter, which is why detectors like Xenon 1T, a vat of ultra-pure liquid xenon buried a mile underground, listen for the faintest whisper of a collision. But after years of hunting, the silence is deafening. Then there's the action, a ghost so lightweight it makes WIMP look like sumo wrestlers. Born from a theory meant to solve an entirely different puzzle in quantum physics, actions could be streaming through you right now, millions per second, with less interaction than a breeze through a screen door. Scientists are crafting exotic action radios to tune into their faint signals, but so far the cosmic airwaves stay quiet. And let's not forget sterile neutrinos, the rebels of the particle world. Unlike their ordinary neutrino siblings, which occasionally chat with matter, these would communicate only through gravity. Some researchers think they might explain odd X-ray signals from distant galaxies, but the evidence hangs by a thread. Now for the wild cards. Could dark matter be made of primordial black holes, forged in the universe's first chaotic seconds? Some tiny, some planet-sized, these ancient relics would drift unseen, their gravity the only clue to their presence. Or what if we're sensing the gravity of an entire shadow universe, parallel to ours but forever out of reach? It sounds like science fiction, but when the alternatives keep coming up empty, even the strangest ideas get a seat at the table. The frustration is real, but so is the thrill. Every null result narrows the hunt. Every bizarre theory pushes us closer to the edge of known physics. Dark matter isn't just hiding, it's teaching us how much we still have to learn. And when we finally catch it, the answer might rewrite the rules of reality itself. Some galaxies shouldn't exist, not according to our theories anyway. Take Dragonfly 44, a shadowy enigma drifting in the Coma cluster. At first glance, it seems ordinary, a faint smudge of starlight barely noticeable next to its radiant galactic neighbors. But when astronomers calculated its mass, the numbers didn't just raise eyebrows, they shattered expectations. This galaxy weighs as much as the Milky Way, yet emits less than 1% of the light. 99.99% of it pure, unfathomable dark matter. How does something like this even form? Picture building a skyscraper where 99 floors are invisible with only a single window lit. Standard galaxy formation models can't explain it. When gas clouds collapse to birth galaxies, dark matter's gravity pulls them together, but stars ignite from the ordinary matter swirling within. Dragonfly 44 flipped that script entirely, almost no stars, just an overwhelming dark matter halo, like a cosmic haunted house with barely any furniture inside. The Hubble Space Telescope first spotted these ghostly oddballs, but it was the James Webb Space Telescope that peeled back another layer of the mystery. Its infrared eyes revealed something even stranger. Many of these dark matter-dominated galaxies are ancient relics from the universe's youth. That's the real head-scratcher. If they formed early, why didn't they collect more gas and stars over billions of years? Were they starved from birth, or did some unseen force siphon away their luminous material? One theory suggests they're failed galaxies, places where dark matter's grip was too weak to hold onto gas long enough for stars to flourish. Another proposes they're the mangled remnants of violent collisions, their stars ripped away by passing galaxies, leaving only their dark matter skeletons behind. But Dragonfly 44 doesn't show the scars of such trauma. It's pristine, undisturbed, a silent rebuke to our assumptions. Then there's the kicker. Some of these galaxies spin too fast for their scant starlight, as if their dark matter isn't just abundant but packed differently than in typical galaxies. Are we looking at a new class of objects entirely, or is dark matter itself more complex than we thought, clumping or interacting in ways our models don't account for? Every answer leads to 10 new questions. What's clear is this: the universe keeps forging exceptions to every rule we write. And with each ghost galaxy we uncover, we're forced to wonder, are these cosmic accidents, or is dark matter playing a game we haven't even learned the rules to yet? Astronomers are locked in a cosmic courtroom drama, and the star-witnessed dark matter might be lying under oath. Here's the problem. Two of our most trusted methods for measuring the universe's expansion rate disagree catastrophically. One method, using distant supernova as mile markers, suggests the cosmos is ballooning at 73 kilometers per second per megaparsec. The other, studying the afterglow of the Big Bang with instruments like the Planck satellite, insists it's 67. That 6-kilometer gap might sound trivial, but in cosmology, it's like arguing whether a bullet train is moving at 300 or 400 miles per hour. The implications rewrite the rules. Enter dark matter's secret alibi. Could its properties hold the key to this discrepancy? Some theorists propose an audacious fix. What if dark matter isn't the unchanging anchor we assume it to be? Imagine a scenario where dark matter decays over time, shedding mass like a melting iceberg. This decaying dark matter model subtly alters the gravitational scaffolding of the early universe, tweaking the expansion rate just enough to bridge the divide between the Planck and supernova measurements. It's a delicate adjustment, like tuning a piano string to harmonize two clashing notes. Then there's the early dark energy hypothesis, a cosmic wildcard. Picture dark matter's enigmatic cousin, a fleeting force that surged during the universe's toddler years before vanishing without a trace. This brief but potent push could have accelerated expansion early on, leaving Planck's snapshot of the infant cosmos looking slower than today's sprinting universe. It's as if the cosmos had a caffeine boost in its youth, and we're only now noticing the jitters, but not everyone's convinced. Critics argue these fixes feel like epicycles, clumsy patches slapped onto a creaking theory. If dark energy or dark matter can shapeshift to solve every puzzle, does that make them scientific explanations or just cosmic duct tape? The Hubble tension isn't just a number crunch, it's a stress test for our entire understanding of physics. Every proposed solution forces us to ask, are we missing something fundamental about dark matter's nature, or is the universe deliberately messing with our equations? One thing's certain: the Hubble tension is more than a mathematical hiccup. It's a flashing neon sign pointing to gaps in our knowledge. Whether the answer lies in rebellious dark matter, phantom energy, or something even stranger, this crisis isn't just about the universe's speed. It's about whether we've been reading its deepest rhythms all wrong. What if the very reason you exist, the atoms in your body, the planet beneath your feet, the sun warming your skin, traces back to an invisible cosmic architect? Dark matter's gravitational embrace didn't just shape galaxies, it might have set the stage for life itself. Picture the early universe as a vast, uneven sea of gas and dark matter. Without those invisible tendrils pulling matter together, ordinary atoms would have remained adrift, too sparse to ignite stars or forge planets. The Milky Way owes its spiral arms to dark matter's steady hand, its gravity creating the dense pockets where stellar nurseries could flourish. No dark matter, no stars, no carbon, oxygen, or the building blocks of life. Yet the cosmos plays favorites. Venture into a dark matter desert, one of those eerie voids like the Boötes void, and the story changes. Here, galaxies are lonely islands separated by unimaginable gulfs, their stars too few to seed life-bearing worlds. Planets in these wastelands would orbit dim, aging stars, their skies nearly black, their chemistry stalled by a lack of heavy elements forged in stellar explosions. Life here would face a cosmic uphill battle, starved of the energy and raw materials that Earth enjoys. This cosmic inequality fuels the anthropic principle debate. Is our universe fine-tuned for life, or are we just winners of a blind lottery? Some argue dark matter's exact properties had to fall within a narrow range for galaxies like ours to form at all, a suspiciously convenient setup. Skeptics counter that we're simply observing the one universe out of countless possibilities where the dice rolled in life's favor. After all, in a cosmos without dark matter, no one would be around to wonder why it's missing. The deeper mystery, dark matter might not just enable life, it could dictate its fate. Simulations show galaxies born in dense dark matter hubs evolve faster, their stars aging violently and dying young. Meanwhile, galaxies like ours, perched on the web's quieter strands, enjoy slower, steadier lives, granting time for planets to mature and complex chemistry to unfold. So the next time you gaze at the night sky, remember, the darkness between the stars isn't empty. It's the unseen loom that wove the tapestry of existence and your place in it. 66 million years ago, a mountain-sized comet slammed into Earth with the force of 1 billion nuclear bombs, blotting out the sun and dooming the dinosaurs to extinction. But what if that catastrophic impact wasn't just bad luck? What if it was orchestrated by an invisible hand from the galactic shadows? Enter the most provocative dark matter theory of all, that our solar system's periodic brushes with death might be written into the Milky Way's hidden architecture. Harvard physicist Lisa Randall proposed a spine-chilling twist on this ancient murder mystery. She suggests our galaxy harbors a dense disk of dark matter, an unseen platter lurking in the Milky Way's midplane, warping space with its gravity. Every 30 to 40 million years, as the sun bobs up and down through the galaxy on its orbital path, it could pass through this shadowy layer. Each crossing, Randall argues, might unleash chaos. The disk's gravitational jolt could disturb icy bodies in the distant Oort cloud, sending a hail of comets hurtling toward the inner solar system, a celestial shower with Earth in the crosshairs. The timing is eerily precise. Fossil records show mass extinctions recurring roughly every 35 million years like clockwork. The most notorious, the Cretaceous Paleogene event that wiped out the dinosaurs, fits neatly into this cycle. Even the crater ages of Earth's largest impacts align with these intervals. Is this just cosmic coincidence or dark matter's fingerprints on the scales of fate? Not everyone's convinced. Critics point out there's no direct evidence for Randall's dark disk. Our galaxy's gravity maps don't yet show this phantom layer. Others argue that passing through a diffuse dark matter halo wouldn't pack enough punch to stir the Oort cloud. The solar system's periodic dips through the Milky Way's crowded midplane, they say, could trigger comet storms without invoking exotic physics. Regular matter, dense gas clouds, rogue stars might be culprit enough, yet the hypothesis refuses to die. New studies suggest subtle wrinkles in the Milky Way's outer stars could hint at the disk's presence. If future telescopes spot these telltale warps, or if we find that comet impacts cluster around specific galactic phases, Randall's idea might shift from fringe to forefront. For now, it remains a haunting what if that the rise and fall of life on Earth may hinge on an invisible rhythm, orchestrated by the universe's most elusive substance. One thing's certain: the next time our solar system surfs through that dark disk, we'll be blissfully unaware until the comets start falling. Dark matter was supposed to be the universe's ultimate architect, slow, methodical, and predictable. Scientists called it cold dark matter for a reason, picturing sluggish particles lumbering through the cosmos, gradually pooling under gravity's pull to form the seeds of galaxies. This slow dance should have created a neat hierarchy, vast halos of dark matter hosting massive galaxies with smaller clumps spawning orbiting dwarfs. But the universe, as usual, had other plans. When astronomers ran supercomputer simulations based on this cold model, they hit a snag. The virtual cosmos produced far more tiny dark matter clumps than we observe as satellite galaxies around the Milky Way. It's like planting a field expecting a dozen trees, only to find thousands of saplings sprouting instead. This glaring mismatch became known as the missing satellites problem. Where are all those phantom galaxies our simulations insist should exist? Some suggested they're simply too dim to see, their stars snuffed out by eons of cosmic turbulence. Others proposed that fierce ultraviolet radiation in the early universe sterilized these dwarfs, preventing them from forming stars at all. But then the James Webb Space Telescope turned the mystery inside out. Its infrared gaze pierced the dust of the early cosmos, revealing galaxies brighter, larger, and more numerous than anyone predicted. These primordial giants shouldn't have had time to assemble under cold dark matter's sluggish rules. Now the puzzle has flipped. Instead of too few satellites, we're facing too many massive galaxies too soon. It's as if the universe's construction crew ignored the blueprints, erecting skyscrapers before the foundations were laid. Could dark matter be warmer than we thought, its particles zipping around fast enough to delay small-scale clumping? Or does ordinary matter play a more aggressive role, with superheated gas rushing to form stars before dark matter's gravity can tidy up? The stakes couldn't be higher. If cold dark matter stumbles here, it might mean tweaking our models or rewriting them entirely. Every unanswered question is a crack in the foundation of modern cosmology. And with JWST peeling back the universe's infancy layer by layer, we're not just hunting for missing satellites anymore. We're staring into the cradle of creation itself, wondering if we've misread the cosmic recipe from the start. Einstein's theory of general relativity has been the gold standard of cosmic gravity for over a century, a masterpiece of mathematics that predicts how planets orbit, light bends, and time warps under the weight of matter. But dark matter's cosmic web is now pulling at its seams, revealing cracks in our understanding of how the universe truly works. Picture a spider's silk trembling as something far heavier than expected tugs at its threads. That's the tension brewing between relativity's elegant equations and the chaotic reality of dark matter's hidden architecture. Take the phenomenon astronomers call dark flow. Like leaves caught in a river's current, entire clusters of galaxies, thousands of them, are drifting toward a single patch of space at baffling speeds. Not just drifting, but rushing. Some unseen force far beyond the pull of any known supercluster seems to be herding them. This isn't just a mystery, it's a direct challenge to Einstein's framework, which assumes gravity's influence fades with distance. Yet here we are, watching chunks of the universe move as if yanked by ropes we can't see. One explanation: dark matter's web might stretch far beyond what we've mapped, with filaments so massive they warp spacetime on scales relativity never accounted for. Simulations suggest these tendrils could extend into neighboring universes, hypothetical regions of space disconnected from our own, their gravitational whispers tugging at everything in reach. It's as if we've been studying a single tree while ignoring the forest bending its branches, but the plot thickens. Some galaxies move too fast for their apparent mass, like race cars with invisible engines. Others rotate in ways that defy relativity's predictions unless we inject dark matter into the equations like cosmic duct tape. The kicker, even Einstein's prized gravitational waves, ripples in spacetime itself, don't behave quite as expected when filtered through dark matter's labyrinth. Critics argue this isn't a crisis, just growing pains. Maybe dark matter's distribution is clumpier than we thought, or relativity needs subtle tweaks in extreme cosmic environments. Others whisper about more radical ideas. Could gravity itself leak into extra dimensions? Is dark matter interacting with forces we've yet to name? The answers, if they come, won't just solve a puzzle. They'll redefine the rules of the cosmos and our place within it. Deep in the constellation Pisces, a cosmic ghost left its mark, not in starlight, but in the twisted fabric of space itself. The galaxy cluster CL0024+17 appeared ordinary at first glance, until astronomers noticed something chilling in its gravitational fingerprint. The cluster's mass, mapped by the way it bent light from galaxies behind it, revealed a perfect ring of dark matter hanging in space 2.6 million light-years wide, like a colossal ripple frozen in an invisible pond. This wasn't just strange, it defied everything we thought we knew about dark matter's behavior. Rings imply motion, collision, energy, things dark matter famously ignores. The leading theory, two massive clusters might have slammed into each other head-on, their dark matter halos passing through one another like phantom freight trains. The gravitational shockwave could have sent dark matter surging outward in a circular tsunami, leaving this eerie imprint. Supporting this, X-ray telescopes found ordinary gas, the cluster's visible matter piled up at the collision center, exactly as expected when gas particles crash and stall, while the dark matter sailed ahead undisturbed. But skeptics pounced. Could the ring be a trick of perspective? Like holding up a hula hoop and mistaking its curve for a true circle, the ring might be a warped projection of a distant dark matter shell. Advanced simulations fueled the debate, showing how certain cluster alignments could mimic a ring's signature without any collision at all. Then came the curveball. Other clusters, like ZWCL 0024+1652, showed similar lensing patterns, dark matter seemingly arranged in arcs and shells. If these were all illusions, the odds of multiple clusters conspiring to fool us felt astronomical. Yet if they're real, why don't all colliding clusters leave such stark rings? The answer might lie in timing. CL0024's ring could be a snapshot of a specific phase in a collision's aftermath, a fleeting cosmic moment we were just lucky enough to catch. The ring's mystery cuts to the heart of dark matter's enigma. Is it truly as indifferent as we think, or does it harbor hidden interactions we've yet to grasp? Every unexplained filament, every ghostly halo, and now this phantom ring whispers the same unsettling truth. We're still just learning the rules of the game. And the universe, it's playing in dimensions we can't even see. In the cosmic game of hide and seek, dark galaxies are the ultimate masters of stealth. Take Segway 1, a wispy smudge of starlight so faint it was missed for decades, lurking right in our galactic backyard. At first glance, it looks like a handful of aging stars adrift in the Milky Way's glow. But when astronomers measured its gravity, the truth sent shockwaves through astrophysics. This ghostly shred of a galaxy weighs 300,000 times more than its visible stars suggest, meaning it's 99.9% dark matter. A cosmic counterweight where the ordinary universe barely left a trace. How does something like Segway 1 even happen? Picture a galaxy that never got the memo to shine. Billions of years ago, it should have followed the usual script: dark matter's gravity pulling in gas, gas cooling and collapsing into stars, stars lighting up the void. But somewhere the process stalled. Maybe the gas was stripped away by a passing galaxy's tidal forces, leaving Segway 1 starved before it could flourish. Or perhaps it formed in a cosmic dead zone where the density of primordial hydrogen was too thin to ignite star birth. The eeriest possibility, dark matter's own distribution might have played a role. If Segway 1's halo was too smooth, lacking the dense knots needed to jumpstart gas collapse, it could have doomed the galaxy to eternal twilight. These failed galaxies are more than cosmic oddities, they're stress tests for our theories. Cold dark matter models predict countless such halos swarming around every major galaxy, yet we've found only a handful. Are the rest too dark to detect, or does their absence hint at flaws in our understanding? Some simulations suggest dark matter's behavior isn't just passive, it might interact with itself in subtle ways, generating heat that prevents gas from settling. Others argue that ultraviolet radiation from the first stars could have sterilized these halos early on, ionizing their gas before stars could form. Then there's the puzzle of Segway 1's survival. With so little gravity from visible matter, its dark matter halo should have been shredded by the Milky Way's tides long ago. The fact it still exists implies its dark matter is clumpier than models predict, a property that could rewrite how we map the invisible cosmos. Every flicker of starlight from these ghosts is a message in a bottle, carrying clues about dark matter's true nature. And with telescopes like the Vera Rubin Observatory set to uncover thousands more, we might finally learn why some universes are born to shine, while others fade into the dark. Forget everything you thought you knew about dark matter being just a cosmic placeholder. What if it has its own secret chemistry with rules we can't even imagine? Most searchers assume it's made of solitary particles, drifting alone through the void like cosmic hermits. But imagine a twist. Dark matter could be as complex as the ordinary atoms in your body, forming dark atoms bound by invisible forces we've yet to discover. Picture a shadow version of the periodic table with dark protons, dark electrons, even dark molecules dancing in the abyss. This isn't fantasy, it's a serious theory gaining traction as traditional searches come up empty. The classic WIMP hypothesis with its lone heavy particles once seemed elegant, but elegance doesn't guarantee truth. If dark matter interacts via some hidden quantum force, dark electromagnetism, it could explain why we've failed to detect it. Ordinary matter barely notices these interactions, just as you don't feel radio waves passing through you. Experiments like Elusive Zeppelin, buried under a mile of rock to shield from cosmic noise, listen for the faintest tick of a WIMP collision. Yet silence persists. Maybe dark matter isn't just weak, it's shy, communicating only with itself through forces outside our standard model. Here's where it gets wild. Some theorists propose dark matter could clump into exotic structures, dark stars, powered by annihilation of these shadow particles, or even dark planets orbiting unseen dark suns. If dark atoms exist, they might form sprawling nebulae between galaxies, invisible except for their gravitational nudges. Others speculate these particles could have excited states, like atoms absorbing energy, emitting dark photons we'd never see. The irony, we might be surrounded by an entire dark sector as rich as our visible universe, utterly oblivious to its presence. Every null result from detectors isn't just failure, it's a clue pushing us toward stranger possibilities. The universe has never been content with simplicity. Why should its darkest secret be any different? What if dark matter isn't just a cosmic afterthought, but a relic from before time began? Imagine particles so ancient they predate the Big Bang itself, drifting through the birth of our universe like ghosts from a forgotten age. This isn't science fiction. Some theories suggest dark matter might be the last surviving remnants of a prior cosmos, a hidden time capsule carrying secrets from a cycle of existence we can't even fathom. Take Roger Penrose's provocative conformal cyclic cosmology, a model where universes don't just end and begin but transform. In his vision, the distant future of one universe stretches and cools into an infinite, featureless expanse, which then becomes the high-energy singularity of the next Big Bang. But here's the twist: certain particles immune to this cosmic reset could slip through the transition unscathed. Dark matter, with its eerie indifference to light and matter, is the perfect candidate. Picture these shadow particles as cosmic stragglers, untouched by the fiery rebirth of spacetime, carrying imprints of a universe that existed before our own. Then there's the cyclic universe theory, where colliding membranes in higher dimensional space trigger endless Big Bangs. In these models, dark matter could be the debris of earlier collisions, like ash from a phoenix's flames left behind to shape the next cycle. The math even allows for these particles to bear faint scars of their past, subtle asymmetries in their distribution that might one day reveal their extraterrestrial origins. The implications are staggering. If true, dark matter isn't just shaping galaxies, it's a living fossil, whispering clues about realities beyond our own. Some researchers are already scouring the cosmic microwave background for patterns that could hint at pre-Big Bang echoes, while others simulate how such primordial dark matter would clump differently than its younger counterparts. Yet the idea divides physicists. Critics argue that without detectable interactions, these shadow particles might as well be metaphysical. Supporters counter that their silence is the point. They're the universe's ultimate survivors, enduring across eons by refusing to play by ordinary rules. Either way, one thing's clear. If dark matter truly predates existence as we know it, we're not just studying the universe's hidden scaffolding. We're reading its oldest, most guarded diary. Right now, as you watch this, an invisible storm is raging through our solar system, a hurricane of dark matter rushing past Earth at 500 kilometers per second. This isn't some abstract cosmic phenomenon. It's the shredded remains of an ancient dwarf galaxy, torn apart by the Milky Way's gravity billions of years ago, now stretched into a river of pure mystery flowing right through your backyard. Astronomers call it the S1 stream, and it's one of the most tantalizing dark matter experiments nature has ever handed us. Picture a cosmic crime scene. 7 billion years ago, a small galaxy, let's name it Gaia Enceladus, made the fatal mistake of wandering too close to the young Milky Way. Our galaxy's immense gravity ripped it to pieces, scattering its stars into long, looping trails. But the real treasure was left behind. The victim's dark matter halo, now reduced to a vast, diffuse current of invisible particles speeding through the galactic neighborhood. What makes S1 so special isn't just its scale, it's the fact that for once we know exactly where to look. Unlike the diffuse fog of dark matter thought to envelop our galaxy, this stream is concentrated, moving in a predictable path like a fire hose aimed straight at Earth's detectors. The question is, can we feel it? LIGO, the Laser Interferometer Gravitational Wave Observatory, was built to catch spacetime's faintest shivers from colliding black holes billions of light-years away. But some physicists wonder if its exquisitely tuned lasers might pick up something closer to home. As S1's dark matter particles flood past, their collective gravity, though individually weaker than a neutrino's whisper, could theoretically warp spacetime just enough to make LIGO mirrors jiggle in a telltale pattern. It's a long shot, but not impossible. Think of it like standing next to a rushing river. You might not feel each water molecule, but the current's combined force is undeniable. But here's the catch. If LIGO detects nothing, that silence speaks volumes. Either S1's dark matter is too smoothly distributed to create detectable waves, or more intriguingly, it doesn't behave like the heavy, sluggish particles we've been hunting for decades. Alternative theories like ultra-light axions or fuzzy dark matter would leave subtler gravitational footprints. Even a null result helps prune the jungle of possibilities, steering us toward the right path. Meanwhile, other experiments are joining the hunt. Underground detectors like Xeno NNT, designed to catch dark matter particles bumping into xenon atoms, might spot an uptick in collisions as S1 stream sweeps through. Others are scouring the heavens for anomaly stars flickering as dark matter clumps pass in front, or gamma rays flaring from hypothetical dark matter decays. The stakes couldn't be higher. This isn't just about spotting a particle. It's about witnessing the ghostly fingerprint of a long-dead galaxy still echoing through the cosmos. The irony, this hurricane has been blowing for eons. Ancient civilizations gazed at the same stars, unaware of the invisible tide washing over them. Now, armed with quantum sensors and supercomputers, we're finally learning to read the whispers of the dark. Whether S1 delivers answers or deeper riddles, one thing's certain: the storm isn't just passing through. It's rewriting the rules of the hunt. Deep in the heart of our galaxy, something is glowing with forbidden light, a mysterious excess of gamma rays pulsing from the Milky Way's core, defying every known source of energy. Astronomers first spotted this enigma with NASA's Fermi telescope, a strange, diffuse glow radiating from the galactic center with no clear explanation. Supermassive black holes, pulsars, even cosmic rays, none of them account for the signal's peculiar intensity or distribution. But what if this isn't just a cosmic oddity? What if we're witnessing dark matter's death throes, the final flickers of an invisible substance annihilating itself in the darkness? The theory goes like this: if dark matter is made of particles, then those particles might have anti-particle counterparts, just like ordinary matter does. Where these particles meet, they could annihilate in bursts of energy, gamma rays being the telltale signature. This process wouldn't be quick. Over billions of years, as dark matter clumps in galaxy cores, these rare collisions would create a faint but detectable glow. The galactic center GVXS fits the profile eerily well. Its energy spectrum and spatial spread align with predictions for certain dark matter models, particularly those involving WIMP with masses around 60 times that of a proton. But here's the catch: nature loves to muddy the waters. The same region is crowded with millisecond pulsars, ancient stellar corpses spinning hundreds of times per second and spewing gamma rays. Could these, not dark matter, be the culprits? Some studies suggest the excess's patchiness matches what you'd expect from unresolved pulsars, not a smooth dark matter haze. Others counter by pointing to similar gamma ray excesses in other galaxies, like Andromeda, where pulsar populations shouldn't be as dense. The debate is a detective story with competing witnesses, each contradicting the other. Then there's the decay scenario, a slower, quieter demise. Instead of violent collisions, dark matter particles might simply disintegrate over cosmic time, shedding mass like a melting iceberg. This could produce X-rays or gamma rays at specific energies, creating spectral lines that telescopes like Chandra or Fermi could spot. So far, tantalizing hints, like the 3.5 kiloelectronvolt line spotted in galaxy clusters, have come and gone, too faint to confirm. The challenge: cosmic backgrounds are noisy, and dark matter's signal, if it's there, is drowning in the chatter. What makes this mystery so electrifying isn't just the science, it's the stakes. If dark matter decays or annihilates, it means the universe's hidden scaffolding isn't permanent. Structures shaped by dark matter billions of years ago might look very different in the far future as this invisible glue slowly dissolves. Could this process influence galaxy formation, alter the cosmic web structure, even subtly change the expansion rate of the universe? The answers might already be hidden in those gamma rays, waiting for the right telescope, the right algorithm, the right moment to reveal the truth. Until then, the galactic center keeps whispering its secrets, one photon at a time. Here's the cosmic irony: dark matter pulls galaxies together with its invisible grip, while dark energy pushes the universe apart with relentless force. These two opposing titans should have torn the cosmos to shreds, leaving no room for stars, planets, or life. Yet against all odds, they reached an uneasy truce at just the right moment in cosmic history to let galaxies form and life emerge. Is this luck, a fluke of physics, or is there something far stranger at play? Picture the early universe as a tug of war between two invisible giants. Dark matter's gravity dominated first, gathering gas into dense knots where stars could ignite. But around 5 billion years ago, dark energy, that mysterious force accelerating the universe's expansion, began to gain the upper hand. The timing couldn't have been more perfect. Had dark energy taken over too soon, galaxies would have been ripped apart before life could evolve. Too late, and the universe might have collapsed back on itself in a cosmic crunch. Instead, we exist in this razor-thin window where both forces are balanced just enough to let matter clump and space stretch, a Goldilocks zone for complexity. Some physicists suspect this isn't coincidence at all. Enter quintessence, a dynamic cousin of dark energy unlike Einstein's static cosmological constant. This hypothetical field could evolve over time, its strength waxing and waning in response to the universe's expansion. In some models, quintessence naturally synchronizes with dark matter's ebb and flow, creating temporary equilibriums where structure can flourish. Think of it as a cosmic thermostat, subtly adjusting the dials to avoid overcooking or freezing the universe. Others propose an even wilder idea, that dark matter and dark energy aren't separate phenomena at all, but two faces of the same shadowy entity. Imagine a dark fluid that behaves like matter when concentrated, pulling galaxies together, but acts like energy when diffused, driving expansion. This single substance could seamlessly shift its role as the universe evolves, maintaining that precarious balance without fine-tuning. If true, it would rewrite the rules of cosmology, merging two mysteries into one. Yet skeptics warn against seeing design where there might only be dice rolls. In a multiverse where countless universes bubble into existence with random physical constants, ours might simply be the one where the numbers lined up right. No deeper physics required, just the statistical inevitability that somewhere, conditions would permit life to ask these questions. But here's what keeps scientists awake at night. If the balance isn't accidental, what's orchestrating it? Could there be laws governing the dark sector we've yet to uncover? Every galaxy we see, every planet we inhabit, might owe its existence to a hidden dialogue between these two forces. A conspiracy written into the fabric of reality itself. And the closer we look, the more it feels like the universe has been waiting for us to notice. Astronomers have a name for cosmic rule breakers like NGC 1052DF2. They call them see-through galaxies, and this one might be the most unsettling of them all. Floating in the constellation Cetus, it's a wispy, ghostly collection of stars so diffuse you could peer straight through it to the universe beyond. But here's what makes it defy logic. When researchers calculated its mass, they found almost no trace of dark matter. None. Its stars orbit at speeds that match exactly what you'd expect from visible matter alone, as if the universe forgot to sprinkle in its usual hidden ingredient. This discovery sent shockwaves through astrophysics. If dark matter is the universe's invisible scaffolding, holding galaxies together against their own spin, how does a galaxy like DF2 exist without it? One camp argues this is proof dark matter might not be universal, that some galaxies form through entirely different, chaotic processes. Picture a car speeding down a highway with no engine. DF2 shouldn't work, yet there it is, gliding along like gravity's rules don't apply. But skeptics fire back. What if we're just misreading the cosmic ledger? Measuring galactic mass is notoriously tricky, especially for ultra-diffuse galaxies where stars are few and far between. Some suggest DF2 might have been stripped of its dark matter by a violent encounter with a neighboring galaxy, like a tree losing its leaves in a storm. Others propose its dark matter halo is so spread out, our current tools can't detect its subtle gravitational signature. Even DF2's distance measurements, critical for calculating mass, sparked fierce debate, with some teams claiming revised numbers would restore its missing dark matter. Then there's the plot twist. Since DF2's discovery, other dark matter-deficient galaxies have emerged, like NGC 1052DF4 and KKS 2004. Are these cosmic oddballs or part of a hidden pattern? Simulations show that in rare cases, tidal forces could wrench gas and stars away from a galaxy's dark matter, leaving behind a naked remnant. Alternatively, some galaxies might form in regions where dark matter is unusually sparse, like weeds sprouting in barren soil. The stakes are higher than a single galaxy's mystery. If dark matter can be absent, even occasionally, it challenges our most fundamental models of how the universe builds structures. Yet if our measurements are flawed, it means we're still blind to the nuances of the invisible cosmos. Every see-through galaxy forces us to ask, are we missing something profound about dark matter's nature, or are we just learning how little we truly see? Physics has a dirty secret. Some of its most elegant equations are hopelessly lopsided. The Standard Model, our playbook for particles and forces, treats matter and the forces that govern it like separate casts in a play that never interact. But nature abhors imbalance. Enter supersymmetry, or SUSY, the grand mathematical symphony that promised to restore cosmic order by giving every known particle a hidden twin. And here's the kicker: the lightest of these shadow particles could be dark matter itself. Supersymmetry's beauty lies in its symmetry. It posits that for every fermion, the building blocks of matter, like electrons and quarks, there's a boson force carriers like photons, and vice versa. These superpartners would balance the quantum books, solving puzzles like why the Higgs boson is so suspiciously lightweight, but SUSY real magic. The lightest supersymmetric particle, or LSP, would be stable, electrically neutral, and immune to decay, a perfect dark matter candidate. Theorists called it the neutralino, a hypothetical heavyweight that could lurk everywhere unseen, its gravity sculpting galaxies. Yet after decades of hunting, the Large Hadron Collider has turned up empty-handed. SUSY particles were predicted to appear at energy scales the LHC can probe, but beyond the Higgs boson's triumphant discovery in 2012, the machine's collisions have revealed no superpartners. Critics declared SUSY dead. Supporters fired back, maybe we're looking in the wrong place. The truth is messier. SUSY isn't one theory, it's a framework with countless variations. Early models assumed superpartners would be light enough for the LHC to spot, but nature might have tucked them into higher energy regimes just beyond our current reach. Some versions propose stealth SUSY, where particles decay so subtly they mimic background noise. Others suggest the neutralino isn't the lightest supersymmetric particle after all, replaced by something even more elusive like the gravitino, a particle tied to gravity itself. The stakes couldn't be higher. If SUSY is real, it doesn't just explain dark matter. It unifies quantum mechanics and gravity, patches up the Standard Model's holes, and might even hint at string theory's extra dimensions. But if it's wrong, we're back to square one, staring at a universe that refuses to conform to our aesthetic ideals. The LHC's silence isn't just a technical hurdle, it's a cosmic riddle, forcing us to ask, is nature subtly symmetrical in ways we've yet to grasp, or is the universe's hidden structure stranger than even our boldest theories dare imagine? Think of the universe's first moments as a bubbling cauldron of quantum foam, where tiny ripples of energy flickered in and out of existence. These microscopic fluctuations, smaller than atoms, briefer than nanoseconds, should have vanished without a trace. Yet somehow they left fingerprints on the cosmos, stretching billions of light years and shaping everything we see today. Dark matter, it turns out, might be the universe's most meticulous archivist, preserving those primordial whispers in its invisible embrace. The evidence is written in the sky, literally. When astronomers map the cosmic microwave background, that faint glow from the Big Bang's afterparty, they don't see a smooth, uniform haze. Instead, it's a patchwork of hot and cold spots, a cosmic quilt stitched together by gravity's unseen hand. These temperature variations, some warmer, some cooler by mere millionths of a degree, mirror the density fluctuations of the early universe. And here's the kicker: without dark matter's gravitational scaffolding, those subtle wrinkles would have smoothed out long before galaxies could form. Picture it like baking a cake. The initial batter, the quantum foam, has tiny air pockets, random, uneven bubbles. Dark matter acts like a scaffold, holding those bubbles in place as the cake the universe expands and sets. Without it, the cake would rise too evenly, leaving no structure, no texture, just a flat, featureless slab. The lumpiness problem in cosmology asks, why didn't those early quantum dice rolls average out? The answer lies in dark matter's stubborn refusal to dilute. While ordinary matter, protons, electrons, photons, was buffeted by radiation pressure in the universe's first few 100,000 years, dark matter stood firm, its gravity amplifying those initial quantum hiccups into the galaxy-forming seeds we see today. But the plot thickens. Some of those CMB patterns don't quite match our simulations. Certain large-scale fluctuations appear oddly synchronized, as if distant parts of the early universe were somehow in cahoots. Could dark matter's peculiar properties explain this? One radical idea suggests dark matter particles might have interacted with each other in the early cosmos, creating subtle pressure waves that left imprints on the CMB. Others propose these anomalies hint at dark matter's even stranger cousins, particles that decayed long ago, or fields that briefly dominated the universe's expansion before vanishing without a trace. The wildest possibility, these echoes might not be from our Big Bang at all. If cosmic inflation, the universe's explosive growth spurt, truly happened, it could have stretched quantum fluctuations from a previous epoch into cosmic proportions. Dark matter in this scenario isn't just preserving a message, it's delivering a note from a time before time, a relic of realities we can't yet fathom. Every new CMB map, from Planck to future observatories like the Simon's Array, peels back another layer of this mystery. The patterns we see aren't just artifacts of the past, they're a living archive, a cosmic Rosetta Stone waiting to be decoded. And dark matter, it's not just the universe's hidden framework, it's the silent scribe recording secrets from the very first tick of the cosmic clock. Einstein told us all matter bends space-time, but what if dark matter bends it differently? Lurking in the depths of our galaxy could be invisible knots warping the fabric of reality in ways normal matter never could, leaving faint ripples in time itself. Imagine space-time as a trampoline. Place a bowling ball on it, that's a star or black hole, creating a predictable dent. But dark matter, it might be more like a shadowy hand pressing down in ways we can't quite map, a distortion that doesn't play by the rules. Pulsars, the universe's most precise clocks, could be our best detectors for this phantom grip. These spinning neutron stars emit beams of radio waves with metronome-like regularity, some ticking more accurately than atomic clocks. But when dark matter's invisible fingers tweak space-time along their line of sight, those ticks might arrive a fraction of a second early or late, like a pendulum swaying in an unseen breeze. Projects like Nanograv are already listening for these anomalies, not just from individual pulsars, but from networks of them across the Milky Way. If dark matter's distribution is clumpier than we think, say in dense halos around black holes, its gravitational echoes could subtly alter the rhythm of these cosmic timekeepers. Gravitational wave detectors like LIGO might catch even stranger signatures. When two black holes spiral into each other, they send shockwaves through space-time. But if dark matter clusters around them like an invisible fog, those waves could arrive distorted, stretched, or squeezed in ways ordinary matter can't explain. Some theorists speculate dark matter interactions could even generate their own ultra-low frequency gravitational waves, a background hum from the universe's hidden architecture. Here's where it gets eerie. If dark matter warps time itself, could it create localized pockets where clocks tick slower or faster? Not quite time machines, but regions where spacetime's flow is warped by the sheer density of these unseen particles. Picture a galaxy's core where dark matter is thickest might time their drift at a different pace than in the sparse outskirts. The effect would be minuscule, but over billions of years, it could leave cosmic fingerprints in the light from distant quasars or the decay rates of ancient particles. The real twist, we might have already glimpsed this. Some pulsar timing arrays have detected unexplained glitches, tiny deviations in their rhythms that don't fit known physics. Could these be dark matter's fleeting handshake with spacetime? Or perhaps the anomaly lies in gravitational wave data. Certain black hole mergers ring with unexpected overtones, as if something unseen is muffling or amplifying their final cries. Dark matter doesn't just fill space, it might sculpt time itself. And if we're right, the universe's most accurate clocks and most sensitive detectors are about to reveal a side of reality we've never seen before. A dimension where gravity's rules aren't just broken, but rewritten by the invisible majority. We've always assumed life needs atoms, carbon, oxygen, the chemistry of light and matter. But what if biology isn't limited to our tiny corner of reality? Enter the dark matter-life paradox, the spine-tingling possibility that the universe's dominant substance might harbor its own form of existence, thriving in shadows we can't perceive. Theorists like Stephen Wolfram have dared to entertain this thought. Could dark matter's enigmatic particles organize into structures complex enough to compute, adapt, even evolve? Picture a shadow biosphere, not life as we know it, but something stranger, self-replicating patterns in the dark matter web, using forces beyond electromagnetism to store information and propagate. If dark matter interacts weakly with itself, as some models suggest, it could form stable configurations akin to crystals or fluid dynamics, but on cosmic scales. These dark organisms might process gravitational or quantum disturbances the way DNA processes sunlight, building complexity in whispers we've never thought to listen for. The math gets wilder. Wolfram's computational universe theory suggests that any system with the right rules can generate complexity, whether it's cellular automata on a screen or hypothetical dark matter particles obeying hidden physics. In this view, life isn't about molecules, it's about abstract computation. A dark matter halo could, in principle, host algorithms as intricate as a brain's neural networks, just running on different hardware. No cells, no metabolism, just pure information woven into the fabric of spacetime itself. But here's the catch: even if such life exists, how would we know? Our tools detect chemistry, light, energy exchange. A dark matter entity might pulse with activity yet leave no trace in our electromagnetic spectrum. Some researchers propose looking for anomalies, galaxies with unexplained structural quirks, gravitational lensing patterns that seem too organized, or regions where dark matter clumps defy entropy without visible cause. Others speculate these shadow systems might leave subtle thermal fingerprints in the cosmic microwave background, like echoes of a conversation happening just outside our perception. Skeptics, of course, dismiss this as speculative fiction. Life requires energy gradients, replication, mutation, all things dark matter's aloof nature seems to forbid. Yet nature has a habit of surprising us. Once we thought life couldn't exist without sunlight until we found ecosystems thriving in ocean trenches, powered by chemosynthesis. Who's to say the universe hasn't engineered stranger solutions in its darkest corners? The chilling truth: if dark matter life exists, we might be sharing the cosmos with civilizations vast as galaxies, ancient as time, and utterly unaware of our fleeting, luminous flicker. Or worse, they might be watching, waiting, from a dimension where we're the ghosts. What if the universe isn't just watching? What if it's thinking? Some theorists propose an idea so radical it blurs the line between physics and philosophy. That dark matter doesn't just shape galaxies, but might also shape consciousness itself. At first glance, it sounds like science fiction, but the hypothesis rests on an eerie numerical coincidence. The amount of dark matter in the universe is roughly the same scale as the number of synapses in the human brain, around 100 trillion. Could this cosmic symmetry be pure chance, or is there something deeper lurking in the shadows? The theory hinges on quantum brain dynamics, a controversial but tantalizing field suggesting that consciousness arises from tiny vibrations in the brain's microtubules, structures inside neurons. Proponents like physicist Sir Roger Penrose argue these vibrations operate at the quantum level, where particles exist in fuzzy, uncertain states until observed. Now here's the leap. If dark matter interacts weakly with ordinary matter, might it also nudge these quantum processes? Picture an invisible hand gently tilting the scales of perception, tweaking neural pathways in ways we can't yet measure. Some even speculate that dark matter's elusive nature could explain phenomena like intuition or déjà vu, moments when the brain seemingly taps into information it shouldn't have access to. But mainstream science isn't buying it, at least not yet. Critics point out there's zero empirical evidence linking dark matter to cognition. The brain's warm, wet environment is notoriously hostile to quantum coherence, where delicate superpositions collapse almost instantly. Even if dark matter particles flood our heads at every moment, their interactions would be so feeble they'd make a neutrino's touch feel like a punch. Skeptics dismiss the idea as wishful numerology, arguing that equating large numbers with mystical connections is like comparing the grains of sand on a beach to the stars in the sky, a poetic coincidence, nothing more. Yet the mystery deepens when we consider placebo effects and the so-called observer effect in quantum mechanics, where mere observation seems to alter experimental outcomes. Could dark matter be a hidden variable in these puzzles? A handful of renegade researchers suggest that if dark matter forms intricate, self-organizing structures across the cosmos, it might also create faint resonances that subtly influence biological systems. Imagine tuning a radio to a frequency just beyond human hearing. Dark matter's signal might be there, humming beneath the static of reality. The truth is, we're grappling with two enigmas here: the nature of consciousness and the nature of dark matter. Both defy easy explanation, and linking them might be a bridge too far for now. But history has taught us that today's fringe idea can become tomorrow's breakthrough. After all, electromagnetism was once dismissed as an invisible force until we learned to harness it. Whether dark matter plays any role in the symphony of thought remains an open question. But one thing's certain: if the universe's hidden majority is whispering to our minds, we're only just beginning to listen. What if dark matter isn't just hiding in our universe, but leaking into it from another? The wildest theories in physics suggest we might be surrounded by unseen dimensions, curled up like microscopic scrolls, where dark matter could be drifting through cosmic walls we can't perceive. String theory's most mind-bending proposition, the multiverse, might hold the key to this enigma. Imagine our universe as a single slice of bread in an infinite cosmic loaf, with countless other slices hovering just millimeters away in dimensions our senses can't access. What if dark matter is the butter seeping through? Brain cosmology, short for membrane, takes this idea even further. Picture our universe as a three-dimensional brain floating in a higher dimensional space called the bulk. Ordinary matter and light are glued to our brain, trapped like flies on sticky paper. But dark matter, it might be the rare substance that isn't stuck. Some models propose it's a higher dimensional particle that barely notices our brain's existence, only interacting through gravity's faintest tug. Every galaxy's dark matter halo, in this view, could be the shadow of something far larger, an invisible structure spilling into our world from dimensions beyond. The math gets dizzying. Certain string theory variations predict universal extra dimensions, where gravity itself is diluted across multiple brains. Dark matter's odd reluctance to interact with light could simply be because it's not fully here, more like a reflection in a foggy mirror than a true resident of our universe. Some simulations even suggest these higher dimensional particles would naturally clump into filamentary structures eerily resembling the cosmic web we observe. Then there's the parallel universe angle. If the multiverse is real, dark matter might be debris from neighboring cosmic bubbles, leftover remnants of universes that bumped against ours in the distant past, depositing their hidden mass like cosmic driftwood. The Bullet Cluster's bizarre separation of dark and ordinary matter could be a scar from such a collision, a snapshot of two universes brushing past each other in the bulk. Critics argue this is all untestable fantasy. Without empirical evidence, extra dimensions remain as elusive as dark matter itself. But experiments like the Large Hadron Collider are probing for subtle energy disappearances that could hint at particles slipping into other dimensions. And if gravitational waves ever reveal anomalies, ripples moving faster than light in a vacuum, it might suggest shortcuts through hidden spatial folds. Whether these ideas hold up or not, one thing's clear: dark matter's stubborn invisibility forces us to consider possibilities that sound ripped from science fiction. The universe's greatest secret might not just be what dark matter is, but where it's really coming from. And the answer could rewrite not just cosmology, but reality's very rulebook. Imagine the universe's final act, a stage growing colder, darker, emptier with each passing eon. Stars burn out, black holes evaporate, and even protons decay into faint whispers of radiation. But what happens to dark matter, the unseen architect of cosmic structure, when the lights go out for good? Its fate isn't just a footnote in the universe's obituary. It could rewrite the very ending of the story. If the cosmos meets its demise in heat death, a slow, inexorable fade into maximum entropy, dark matter's role becomes eerily passive. Unlike ordinary matter, it doesn't radiate, clump into degenerate remnants, or even interact with the fading glow of photons. It simply lingers, a ghostly audience to the universe's quiet dissolution. Simulations suggest these particles will drift further apart as space stretches, their gravitational bonds weakening until each one becomes an island, isolated by unimaginable distances. Yet here's the twist: even in this frozen twilight, dark matter's gravity might still sculpt the void. The last structures in existence could be vast, diffuse halos of dark matter, outlasting galaxies by trillions of years, their slow dance the only motion left in a near-static cosmos. But what if the universe collapses instead? In the Big Crunch scenario, where expansion reverses into a catastrophic implosion, dark matter becomes the ultimate puppet master. As galaxies merge and space contracts, its gravitational pull accelerates the collapse, dragging ordinary matter into the maelstrom. Some theories suggest dark matter particles could annihilate upon contact in this high-energy finale, unleashing bursts of radiation that briefly light up the cosmos's dying moments. Others propose it might trigger the formation of supermassive black holes, which then dominate the universe's final seconds. Then there's the wild card: dark matter's potential instability. If these particles aren't perfectly eternal, they could decay over googles of years, releasing energy that subtly alters the universe's dying breaths. Picture a lightless sky flickering with the last sparks of dark matter's transformation, a final cosmic sigh before absolute stillness. Alternatively, if dark matter interacts with itself in ways we've yet to discover, it might clump into exotic remnants, dark black holes, or strange quantum condensates, outliving everything else in the cold, dark depths of time. The chilling reality: dark matter's fate is tied to questions we can't yet answer. Is the universe destined for infinite expansion or cyclical rebirth? Does dark energy's acceleration have an expiration date? The answers lie in the invisible majority's hands. One thing's certain: when the last star winks out, dark matter will still be there, silent, enigmatic, and far more than a spectator. It's the universe's ultimate survivor, and its final act might hold the keys to realities beyond our own. From galaxies spinning too fast to invisible rings spanning millions of light years, from phantom particles that refuse to interact to secret dimensions leaking into our universe, dark matter has defied every attempt to pin it down. We've uncovered 25 staggering mysteries, and yet the cosmos seems to whisper, "You've barely scratched the surface." Think about that for a moment. Everything we see, every star, every planet, every speck of dust accounts for less than 5% of the universe's total content. The rest, a cosmic void filled with questions. Why do some galaxies orbit as if tugged by invisible strings? How does dark matter sculpt spacetime itself? Could it be alive, thinking, or even a relic from a universe before our own? The more we learn, the more the shadows deepen. But here's the beautiful part: we're living in a golden age of discovery. Telescopes like James Webb and experiments like LUX Zeppelin are peeling back layers of the unknown, turning what was once science fiction into tomorrow's breakthroughs. Every null result, every anomaly, every unexplained flicker of light is a clue, a breadcrumb leading us closer to the truth, and that's where you come in. Stay curious, ask questions, look up at the night sky and wonder what's really out there, lurking in the dark. If these mysteries hooked you, imagine what's still to come. Hit subscribe so you don't miss the next cosmic revelation, and drop your favorite enigma in the comments. Was it the ghostly galaxies devoid of dark matter, the eerie possibility of dark life, or the spine-tingling notion that we're surrounded by dimensions we can't even perceive? The conversation doesn't end here. As we fade out, watch this: a supercomputer's vision of the cosmic web, tendrils of dark matter weaving the universe into existence. Every glowing node, every dark filament is a reminder we're not just observers. We're detectives in the greatest mystery of all time, and the next clue could be just one observation away.